Record. All right, welcome back to System Software. So we're going over our first project for the compiler, which is translating arithmetic, and branching operations. Last time we went over arithmetic operations. So what simple IR looks like, its semantics, what potential equivalent assembly instructions look like, and went over a little bit of the details of x86 64 assembly that you need to know for generating the compiler. Questions on the compiler project, question on the lectures last time, any of the last lectures, questions on the idea behind the compiler project? Yeah.
I had a question for going on the code gen when it says both the functions that were given to you and the functions that were hard coded. What exactly is the difference? Are we changing anything with the ones given to us, or are we just inputting the code in this new editor?
Yeah, you'll just copy that code into your compiler, or replace the. So let me get to that section. So for this project, it's the same. You'll take this code, this implementation of the enter unit function, and just copy it in. Just use that implementation. For the hard-coded ones, these are, you do the same thing. You just copy this implementation. But you'll only do this for CodeGen 1 and CodeGen 2. For CodeGen 3, you're going to have to write these functions on your own, enter function. So for CodeGen 3, which we haven't even talked about yet, you won't be able to just copy this. You'll have to write your own implementation of it. Okay. The reason for that, when I say hard-coded, I mean that the ones given to you, these will work for all simple IR programs. The hard-coded ones, these will only work for a single simple IR program. Oops. These will only work for this program. So you see the difference? So the overall goal of your compiler is to take any simple IR program, which could have a million different if gotos in it, could have one if goto, could have thousands of additions, could have one addition, could have no additions, any simple IR program, and translate it to an equivalent assembly program. To make it so that you can implement CodeGen 1 and CodeGen 2 separately without having to implement CodeGen 3, I've given you implementations that only work for a single simple IR program, just that you can test arithmetic and branching and pointers. Does that kind of make sense? Yes. So it's as if somebody you wrote a C program and you have a single ASM translation of it. That's not the same thing as a compiler that will take any C program and give you the equivalent machine code. So yeah, operationally for you, when doing this project, just take all of these functions and just copy them in to your compiler. And these are the only 4 functions you actually have to implement on your own from scratch. But yeah, good clarifying question. Other questions on the project? Yeah.
Will any of the CodeGen projects have bonus points?
No, I don't have any bonus points for these. But if you have an idea, let me know if you have any ideas for bonus. But no, I don't have bonus points for these. So the syllabus only outlines, how many bonus points was it? So Proc and FS have 2 points each, and then 2 points for the attendance. So yeah, 6 points total for bonus. So the total is 106 out of 100 possible for this class. Yeah?
Not about CodeGen, but about Proc, I think. When can we expect to have those regraded?
Proc regrading by the end of the week.
Okay.
They should be graded by the end of the week. Or come to office hours, and we can do it by hand for you. Yeah?
Can we get bonus points with the regrade?
Yes. Yeah, you can still get bonus points with the regrade. So there's up to 2 points for Proc and FS. So if you got perfect and all bonus points, you get a 9 out of 8. So even if you turn it in late, you can still get over 100% on the Proc and FS projects. Yeah, absolutely. So yeah, this class is designed to incentivize you to turn stuff on time, but also not completely penalize you, destroy your grade if you resubmit it. So there's 6 projects, so that means there are 6 potential late points, but there's also 6 bonus points, total bonus points, so you can always recover your grade. All right, other questions on the project? And just as a reminder of the basics of the project, the goal of this project, this is very ugly, but the goal of this project is to write this compiler. And the compiler will take in simple IR source code, it'll take in a program written in that language, and it'll output an assembly program. So when you're writing your compiler, you're not doing addition, you're not writing C++ code to do addition or to do subtraction. You're literally just doing printf, or in the case of C++, C out, but you're literally doing just writing to text. You're writing out text. And that text is supposed to be correct assembly code. Any questions on this concept? I think I just kind of harped on this quite a bit last week. But any questions on that idea? Maybe it's easy to look at, but when you actually go to code this, it's a little tricky, right? Because how do you test your compiler? There's an infinite number of potential programs. And you have to do a bunch of work to actually test the output. You have to compile the output of the program. But I think I've given you examples of doing, actually using your compiler, which is somewhere. So this actually walks you through how to use your compiler. So just like with GCC, you have to translate your program first before you can actually run it. Here, since remember we're doing only the compile step, we're not doing the linking step here. This is how you compile a program from simple IR into assembly. And then you can use GCC, which will invoke the assembler and the linker for you. And that will give you an executable program, and then you can execute the program. This is how you can see the exit code. But you can also do reading and writing of numbers, which is, I think, detailed in the handbook as well. So if you want to do reading and writing input and output numbers, you can use this template example. Will show you an example of doing that. So here we just link with our little IO library, which has print it and read it. But yeah, actually this template will already do print it for you, so you can test that way. Questions on the project? Questions on arithmetic? Like compiling arithmetic, I mean. All right. Has anyone gotten started on the CodeGen project? Or are you still struggling with this? Okay, not many people. So maybe there'll be more questions once people work on the CodeGen project. All right. All right, let's do homework. Homework 19. All right, the x86-64 instruction sets IDiv operation for integer division. It only takes a single argument. So for instance, IDiv RBX. What's RBX here? What's that? What's that? I'm hearing divisor. Yeah, it is the divisor. But just to make it clear from the architecture, this is a register. This is a register in the x86 world. But yes, this is is it the divisor? Is that the right word? Yeah, the divisor. Okay, it only takes a single argument, but division takes two arguments, right? The numerator and the denominator. How do you set the other argument? Yeah, you just set RAX. So in this architecture, the numerator is hard-coded at the architecture level to always use the RAX register. Yeah?
You also have to sign extended.
Yes, you have to sign extended. Yeah, you have to run the CDQ operation to turn it, because IDiv really takes a 128-bit numerator, and that's all CDQ does. But yeah, that's right. That's right. That's how you set the other argument. Yeah, right. You'd use copy the value into RAX and then do CDQ to turn it into a 128-bit number composed of RDX and RAX. Other questions on this? Yeah.
I want to clarify what you said. Because I thought, was he saying, because you're going to do sign or unsigned division, right?
You can, but well, okay, so we can actually look. I can show you the documentation of this. So the problem here is that, dividend, divisor, I can't remember these words. So the dividend that the IDiv operation will take is actually broken up into two registers. So it's not just going to take RAX, it's going to take whatever is in RDX and RAX. So if you have some random value in RDX, you're not going to be dividing RAX alone. It's going to be working on 128-bit 128-bit number. Does that kind of make sense? So the high 28 bits, high 64 bits is going to be an RDX. The low 64 bits is going to be an RAX. So if you just want to have a 64-bit number, just RAX as the dividend, the way you can avoid having to deal with the whole 128-bit number thing is to run this operation, CDQ. So CDQ is here, convert word to double word. So I don't remember any of these. I don't remember any of these like prefixes, but it's going to take. EX. Actually, it's going to be 32-bit. I might have the wrong operation here, but anyway, it's going to take whatever is in RAX. Actually, it should be CDO. Now that I realize it. Well, we're not going to have any numbers large enough to deal with this, but it's going to just sign extend the A register into the D register. But it should be CQO actually. Oh well. But so it'll work with 32-bit numbers. So don't use anything above a 32-bit number, and it'll still work. All right. Any other questions on this? So I mean, at the end of the day, just take your dividend and put it into RAX and use CDQ or CQO, which is actually what you're actually supposed to do, and then division will use that as the numerator. That 64-bit or 128-bit numerator. Other questions on this? This is me, not RTFM. All right, other questions on the homework? All right, let's take attendance. Okay, let's get into translating branching statements. So the goal here is to take simple IR programs, which are written in this language. So we have the label followed by colon. For instance, this is an unconditional branch. It will use the goto keyword and then the name of a label, any label in your simple IR program. Questions on the meaning of this, the so-called semantics of this, the meaning of this unconditional branch? I think everyone should have seen this in computer organization. The goal is to take simple IR programs and translate them into assembly. So in assembly, the semantics is really similar of unconditional branch in assembly language, not necessarily machine code. In assembly, you have a label, also defined using a name followed by a colon, but you use JMP as the opcode for branch. So for unconditional branches, the translation looks pretty easy, right? I think you could probably hack together a program to do this translation. You just look for the goto keyword, translate it to JMP. But that's the overall goal. We're translating between languages. They only have a very slight difference here, but they're still different languages. Goto is not a keyword in x86, 64 assembly language, so this program will not be translatable into machine code. Will not be you can't create an executable out of it using an assembler. All right, any questions on the goal here? So we're just translating, just like with arithmetic, everything with the compiler, we're translating from simple IR into assembly. Questions on this example? Okay. Okay. So in the x86 world, labels are named locations in the code. When this gets turned to machine code, what will these labels get translated into? If we're in the machine code world, how does a branch, yeah, was it? Binary. Okay, the binary, what does the binary mean? So it's all binary, right? We talked about last time. Sound data, numbers, floating point integers, it's all binary. But what does that binary mean? What is it referring to? Is it an integer? Is it a floating point number? Is it a piece of music? So if you have a branch in MIPS, what are we branching to? You can call it an int, but where are we branching to? Where's the code stored? Stored in RAM, right? And how do you refer to a slot in RAM? Yeah. No, the stack is also in RAM. But how do you refer to an address in? Yeah, it's an address. Yeah, it's an address. So this jump instruction, this is going to be assembled into the jump opcode, which is going to be some number. And the address is going to be, or the label is going to be translated into an address. That's what's going to be translated under the hood. That's like computer org stuff, right? So it just updates the program counter, changes where the program counter is going to start reading from instructions from next. Okay. But for us, we're working at the assembly level, so we can just use named labels. And you put a named label, and then wherever you use a branch instruction, the assembler will work out what address. I think there are several different branching instructions in the Intel world, but there are relative addresses, so it'll be a relative offset from your current instruction. But anyway, there's details, architectural details we don't need to worry about here. But yeah, you just make a label for a named location. This is the x86 64 assembly mnemonic for the unconditional branch. As long as you have a label defined in your assembly file, you can just use JMP to branch unconditionally to it. All right, questions on this? Okay, so what about conditional branches? So we have a goto in C, an unconditional branch. What about conditional branches? How do we write code like this in the assembly world? So if you never looked at x86, what about MIPS? How did you do a conditional branch in MIPS? Okay, so you had like branch if something is equal. Actually, I don't know MIPS, so what is the format of that opcode? Do you have to put in the registers to compare? Okay, so yeah, MIPS is probably a little easier to work with. In the okay, so first of all, in the actually I didn't even show it here. This is a little out of order, but in the x86 world, we have similar instructions like BEQ. Instead, we have jump LE or jump E for equals. But notice all it takes is a label. So it looks like an unconditional branch in terms of the format of the argument. But in the Intel world, the way you do it is you run a comparison operation first, or really any operation. You run a compare, and then these jump commands, they will look at a hidden register, a flag register, that will store the state of this comparison. So when you run the compare operation, a flag register in the chip is going to be set to a value that allows the branch instruction to check whether the last instruction was less than or equal to, greater than, etc. So same idea as MIPS, just two instructions instead of one. But that's the difference, between MIPS and the Intel world. But this is an example of what a conditional branch will look like. We need to use two instructions to do it. All right, questions on that? All right, so we looked at what a C-like conditional control flow statement looks like in simple IR, but let's go over it again here. I think we looked at this like two lectures ago. But let me go over it again, just so you'll understand simple IR, you'll know how to write simple IR programs for testing. So this is our C program. We read in an integer to x, and the statement says if x is greater than 10, then we run this statement, we set x to 11. Otherwise, we do nothing. And then once this conditional statement is done, for any path through this program, we increment x by 1 and print x. This is a fabricated program. It's kind of meaningless, but any questions on what this code does, like operationally, step by step, what it does? So it reads in an integer and sets it to be maximum of 12 if it's above 10. Otherwise, it sets it to the number, just keeps it, increments the number by 1. Questions on this code, the sequence of code? Okay, let's look at the simple IR version of this. So simple IR, each simple IR file is a single function. So this is the function main. In order to get the result of one of the print. So in this language, every function call has to have a result, has to have a variable that it's set to. So I make a new variable to hold the value of print int, but we only have two variables here, x and result. Yeah.
So false label ends whenever you input results. So I'm looking at to see like where exactly. So it's calling. It says go to false label, and I see it's called false label. Where do you know exactly where false label ends?
Oh, false label doesn't end. Yeah, so this is, once it jumps here, that's it. You're done. The processor will just continue executing the code sequentially until it reaches another branch. So this illustrates the difference between so-called structured programming in the C and high-level language world, where we define code blocks that will all run together. But in the machine code world, the only way we can affect control flow is with branching, is to set the program counter to be a different address. That's all we get in the architecture world to do branching. So yeah, false label doesn't end. That's actually the tricky. So we don't do it in this class, but that's one of the tricky parts, or the insightful parts of translating high-level languages into assembly. Is that this kind of structured code, like nested constructs, even functions, they don't exist. You can't express those things at the architecture level. So the job of the compiler is to translate these constructs, which aren't supported by the architecture, and translate it into an equivalent program that is supported by the architecture. So that's why we just have to use gotos everywhere for the translation of this into machine code. Does that kind of answer your question? So yeah, there's no block here called false label. It's just, if this condition doesn't match, skip the body of the if statement, and then just continue executing the program from that point. So simple IR has about the same level of language support that x86 has. There's no structured programming. You only have a goto for branching. But in this class, we're not going to have to do this translation from C to this. Yeah.
One more thing.
Yeah.
I noticed for the C code, it said x is greater than 10, but for the assembly, it's saying it's less than or equal to.
That's a good question. So we briefly touched on this like last week, but I wanted to go over this again to make this clear. So let's do an example executing this program. So let's say we read in the number. Let's do 5. So x equals 5, and then we get to this condition. Is x greater than or equal to 10, or greater than 10? No, right? So the next thing that should run is x plus equals 1, and then x will be 6. Makes sense, right? So let's run this. So this is in C. This is in the C program. So let's do the same thing for the simple IR program. X equals 5. Now, is 5 less than or equal to 10? Yes. So we branch here to the false label. And what's the next instruction? Well, it's x equals x plus 1, and that gives us 6. Same answer, right? So even though, kind of linguistically, they look different, we get the same answer. Now, that doesn't prove that they're equivalent, but it proves that, at least for this test case, they are equivalent. Let's do this for x equals 20. So in C, 20 is greater than 10, so then x equals 11, and then we have x plus equals 1, and we get 12. With me on that? In the simple IR version of the program, if we have x equals 20, then 20 is not less than or equal to 10, so what's the next instruction? So we don't do this branch, right? This branch only happens if x is less than or equal to 10. We don't do the branch, so we go to the next line, which sets x to 11, the next line, it's labeled false label, but there's no executable content here. It just goes to the next line of code, which is x equals x plus 1. And we get 12. So for both these programs, or both these inputs, the program is equivalent, right? So we invert it because, you don't have to. You can write an equivalent assembly program in multiple ways, but the common way to do this in the compiler is to invert the condition and then go to the else branch or go past the if statement if the inside is true. But just as an exercise, since it's kind of an interesting question, could we write this program in a way where we use the same condition? So this would be like the true label. Can we write, an alternative simple IR that's also equivalent? Is it possible? What do you think? So how would we write this? So would this be x equals 11 here? No, I see some shaking heads. No. Because if x is greater than 10, what do we want to do? We want to run x equals 11. So somewhere down here we want to run x equals 11. True label, yeah, good. So we want to run x equals 11 if this condition holds. So we're going to branch to x equals 11. But if x is less than 10, this is going to be the next line of code. So what do we have to put here? So if we don't put anything here, what's going to happen? It's going to run x equals 11 again. So, oops. So in this case, if x equals 5, then the result should be 6. But here, if x equals 5, we're going to go here, and then the next instruction will be this. So x will be 11. It'll be wrong, right? So how can we avoid that? Add another label. So we can have another label, like say maybe end label. And what do we do with that label? Right, we're going to need to do x plus equals 1, but we still have the same problem of if x is 5. So let's say x is 5 here. Let's say x is 5. So this is the running the program. If x is 5, this condition is not going to be triggered. It's just going to go to the next line. But the next line of code sets x to be 11. And then the final line of code will set x to 12. X equals x plus 1. But is this correct? Is this a correct translation of this? No, it's not. So what can we do to make this version of the program where we test for x greater than 10 equivalent to this C program? Yeah, say again. Say again. You can put a go to. Yeah, I think somebody else is saying it. You raised your hand. So yeah, you can put a go to here to kind of create like a virtual block. So we've got a block here for like the else branch here, and we've got a block here for the if branch. And we can use gotos to skip past these branches so that we have like two discrete branches here. Let me actually show an example of it, if then else, so that'll make this a little clearer. I was going to show this more towards the end of the class. I was going to show this anyway, but I think this is a fine time to show it. So let's take a similar program here. Let's say we have this code. So here's our program in C. Let's write this in simple IR. So we're going to have some condition here. Do you want to do x greater than 10 or x less than or equal to 10? All right, let's do if x less than or equal to 10. Go to something. And down here we're going to have two pieces of code that we want to execute depending on whether this condition holds. So let's just be a little pedantic here and give each of these a label. So this is kind of related to the question that your colleague asked about, like, where does the label end? And strictly speaking, the label doesn't end, but we can simulate the behavior of blocks by wrapping each block with a label and a go-to to somewhere. So maybe this answers your question a little better, actually, right? Like, where does it end? So strictly speaking, no, nowhere, because it'll just keep running whatever code it's given. But we can simulate what a structured program looks like in assembly by wrapping blocks of code with labels and go-tos. Does that kind of make sense? You kind of see this structure here? And then it's just the matter of trying to fill out these labels here. So where do we branch to if x is less than or equal to 10 for this program? True label or else label, else branch? Am I confusing you guys? So in the original program, if x is greater than 10, we run x equals -1. Otherwise, we run x equals 2. So if x is the opposite of that, if we run x less than or equal to 10, where do we go? Is that the else condition or the if? What's that? That's the else branch, right? It's the else condition because we inverted it. So a little, hopefully you're not too confused, but here we just inverted the logic. So if the inversion of this, another way to say this is that the else branch is the negation of the if branch, which is the same thing as saying, in this case, x less than or equal to 10. All right, there's a lot of symbols here. So let me not put too many symbols, but yeah, so negation of x greater than 10 is the same thing as x less than or equal to 10. So this is the condition of the else branch. So if that condition is met, then we jump to the else branch. Otherwise, we go to the next line. And the next line is the if branch. If you want to be really pedantic, you could put like another if jump here to go to the true label, but it's like unnecessary. All right, then what about these go-tos here? Where do we branch at the end of each of these? So let's say we have another thing here where we say y equals x. How do we make sure that we reach y equals x after both of these? So no matter which one of these arms of the if statement runs, we always want to run y equals x next. What's that? Yeah, we have the go-to. So we don't have a label yet, though. So we add a label for the section of code that we want to go to after either of these arms runs, and just use that as the branch out of, kind of conceptually out of these two blocks. That sort of makes sense? So again, this was for the end time. This isn't too much of a distraction. I was going to actually go over this close to the end of the class. Go ahead. For the else branch, yes, that's right. So strictly speaking, there's kind of like extra code here. This is like superfluous. But I find it's easier to look at this code, right? This is also superfluous. You actually don't need this branch, so you could remove these branches. But writing it this way makes it much clearer, much more direct translation between this code and this code. And in fact, real-world compilers like LLVM will do something like this. They'll put these apparently unnecessary branches at the end because we care about correctness. It's easy. We want the translation to be correct before we make it optimal. Premature optimization is the root of all evil. You want to do correct before optimal. And in fact, if you take compilers class, you can actually automatically optimize this away. You can write an algorithm that will do this for you. You don't have to be really clever about translating this high level, this C code, into intermediate code. You can do the easy thing and then just write another algorithm that will automatically check for these. They're called peephole optimizations. They will automatically reduce these superfluous commands. And that's actually a lot of what compilers do is optimization. But you don't have to do it in this step. You can first do a really straightforward translation, as straightforward as possible, to intermediate code, and then there are all sorts of fancy algorithms for improving this code automatically. All right, questions on that? Okay. And just to kind of, there's a nice technique also from the compiler world, but also used in like malware analysis, reverse engineering, if you're interested in any like security type stuff, or reverse engineering. There's a really nice, useful data structure from the compiler world called the control flow graph or control flow diagram. And it's really just, and I think you've all doing graphs, right? Or maybe that's CS2. But we can take all of these chunks of code, like this condition check. We can take the two assignment statements, which are in two different blocks, and we can take the set of code that's supposed to run after it, and we can take any code that doesn't have any branches in or out, just the so-called straight line code, the code that runs without any branching coming in or out, and we can compartmentalize those. And then we can represent all the branching behavior with arrows and make a graph. Graph is like a tree, except you can have multiple parents. So it's like a tree, except you can have multiple in-edges to the parent, if you haven't done graphs yet. And this is called a control flow graph. And we can actually analyze, we can see graphically the flow of control through this program, even if it has really complicated conditions. If we kind of factor out the straight line code, the stuff that isn't doing branching, we can visually see this. And this step, this control flow analysis, this is a step in reverse engineering. Because here, we've got unstructured code that has branching behavior. And you can actually decompile assembly code into something like C code using this structure, because it recaptures the original structure of the if statement. Anyway, so this is a little more advanced stuff. I'll show a little bit of this more at the end. I'll show you what all the control flow structures, or what all the control flow constructs look like in C. But this is, if you're interested in reverse engineering or security or malware analysis, this is a really commonly used analysis that's done on code. All right, any questions on this? So CFG for short, control flow graph. So yeah, take like malware analysis, disassembly, decompilation, or compilers class. You can see more about that. All right, any questions on what simple IR looks like, and it's just like MIPS, what simple IR looks like for conditional statements? So I just wanted to give you, from a lot of angles, what these conditional statements look like, so you can like program in them. You can write test cases, and you can understand what they mean when you go to translate it to x86. So how do we translate? So let's take one snippet of this code where we do the conditional goto, and we've got a label with some arithmetic, or with some assignments and arithmetic code around it. So this is from the last lecture, and this code is given to you. We also talked about this in last lecture. But let's see how we can translate this program into assembly. So does anyone remember how we translate accesses to variables like x? So how do we access the data for x in assembly in our translation? What's that? Offsets, yeah, offsets from, remember? So yeah, we had offsets from this special register called RBP, the base pointer. And we're gonna learn that when we do functions. We're gonna learn how we actually set that. But this is supported, this is like the designers of the Intel architecture, and I think MIPS has this as well, actually, a base pointer, or a register that's commonly used for it. But the designers of the architecture were like, it's so common to store local variables in memory as something like an array, that we're gonna create a special register that's devoted to just storing this address in memory. Because this is such a common technique for implementing programming languages, that we have a special register and a special type of operand that we can use to basically do an array index into the RVP array. So we'll see how that actually gets set and managed when we deal with functions, but for now you can just remember that your compiler that I've given to you will create a symbol table of the offsets of each variable in our program, and then all you have to do is generate this assembly operand plugging in the offset from the table. So that's how we access variables. So to access x, or I guess I should say, what variable is this? This is x because it's offset 16. And what does this instruction do? So what's the result of this instruction? How does the state of your machine change, RAM and registers?
RAX gets a restored RBP divided the offset.
Yeah, exactly. So RAX is the only thing that's going to change here, in terms of what's the functional behavior of the CPU. The RAX register is going to change its state, potentially. It's going to be whatever the value of this memory location. And this memory location is given by the address in RBP minus 16 bytes. So RAX is going to change its state, potentially here. All right, questions on this? This is a review of accessing variables. Yeah?
Do you know why it's minus and not like addition?
We'll see this when we look at functions, but it's because the stack grows downward in memory. The heap grows up, stack grows down. So yeah, that's why. We're going to start from a high point in memory, and then the array is kind of moving down in addresses because the stack grows down as you push to it. And we'll see that when we do functions. Okay, so comparing operands is really straightforward. So it's just the compare instruction, and then you give two registers. Compare doesn't actually produce any result. It doesn't change the state of any visible registers. It only changes some flags behind the scenes. The details of this, if you look at the notes and if you're really curious about the architectural details of this, you can take a look at this is in the notes if you want to see the actual reference for this. But all you need to really remember is that you run compare, and then immediately after it, run one of the jump instructions. So this is the table of all the conditional branches, conditional jumps that we're going to use in this class. So you run compare on two registers, and then call a conditional jump. So they're all prefixed by J, and then there's a condition code, one or two letters after it. So E for equals, NE for not equals, L for less than, LE for less than or equal to, G for greater than, GE for greater than or equal to. Questions on this? So to do your conditional branch, run compare, followed by a branch. Okay, let's do a little example of a compare. So let's say I've got so the code in here doesn't really matter, but just a little quiz or a little question. Whoops, man, my typing is bad. All right, in this code, will the branch happen or will the branch not happen? And I actually have to work it out too because I wrote this deliberately to kind of confuse myself or confuse you guys. Will the branch happen or will the branch not happen? Who says the branch will happen? Who says the branch will not happen? Okay, why won't the branch happen? Oh, okay, right, really good, you got it. So this comparison is just like all the other arithmetic operations in AT&T syntax. So this is checking whether, the result of both of these instructions is checking whether RAX is less than RBX. Just like all the other arithmetic operations, the left operand is the second operand of the instruction. So a way to kind of remember this is a compare operation is really just a subtraction. And here's why. And that documentation I showed you, if you want to look at the architectural details of this, a comparison is identical to a subtraction, except it doesn't actually update, doesn't actually store the value. It throws away the value. So it's subtraction, but throw away the result. So it's the same. And how does subtraction work? Well, subtraction is RAX equals RAX minus RBX. But we don't actually save the result. So no result is saved, so it's equivalent to doing RAX equals RBX. And then in the machine, there's a special flag that determines whether the result of this is 0, positive, or negative. So this is some like kind of classic math. So if I'm trying to check whether something is less than something else, that's the same thing as saying RAX minus RBX is less than 0, right? Y'all believe that, I'll accept that, right? And checking whether RAX is greater than RBX is the same thing as checking whether RAX minus RBX is greater than 0. And same thing with equality. So if they're equality, we check whether it's equal to 0. With me on this so far? Did you learn this in computer organization? Did they teach this? They did? Okay, I'm seeing nodding. All right. So I hope so. Maybe some of you don't remember, but some people probably learned this in computer architecture. I mean, this is how you design condition check. So this is, you can just do subtraction and then see whether the result has any of these properties, whether it's greater than 0, less than 0, or equal to 0. And I think you only need less than and 0. You only need 2 of these in order to do all comparisons, to do all of these comparisons. You only need to know whether it's 0 and or less than 0, I think. Correct me if I'm wrong, but I'm pretty sure you only need those 2. Greater than or equal to 0, this one is only a little more complicated. So here, how do you check whether it's, let's say greater than or equal to 0? Well, you check if it's 0 or RX minus RVP is greater than 0. So you can check both of those. All right, anyway, so I don't know if that makes it easy to remember, but you can just, to kind of, if you remember subtraction, then you can remember how to use comparison, because it is just subtraction, except you throw away the result. You don't overwrite RAX. That's what comparison is. All right, questions? Questions on this? Okay, so to implement an if go-to statement in simple IR, all you have to do is translate it to these 2 instructions. Well, okay, for the actual conditional branch part. So assuming that RBX and RAX have already been assigned, then this is what the instruction translates to. Comparison followed by the corresponding jump condition code. Questions on this? All right. So for a complete pattern, a complete template for your translator, whenever you see a simple IR operation that looks like this, where you've got some operand, some operand on the left, some operand on the right, some operator, and the operator is from a predefined list of operators, and then a label. These 4 parts, operand 1, operand 2, operator, and label, these are the only parts that are going to change in the input. These unchangeable parts, if and go to, these are keywords, right? These are the keywords of the language. They never change. They help the compiler see what operation you're asking for. And this is how they roughly correspond to the code here. So you take whatever operand 1 is, populate RAX, take whatever operand 2 is, populate RBX, and then this is hard-coded. You're always going to compare RBX and RAX in our compiler in a simple implementation. This is all that's going to change, is what you put in RAX and RBX. And then the operation, the operator you're going to use, is really translates to the condition code. So you do comparison, and then the operator is actually here. You always do comparison, that never changes. You operate here, and then whatever label the user gave you, that's the label you jump to. Questions on this? This kind of makes sense? All right, good. Okay, good. That's clear. So the idea of doing compilation is pretty tricky and pretty hard to wrap your head around, but a really simple way to do it is to just come up with one pattern that works for all input programs, and then just like hard code as much as you can. Print out, hard code as much of it as you can, and then just only swap out the parts that are different from the input language. So this is part of the reason why if you see my code, that if operator 1 is a constant, I still do a move operation. I still move that constant into RAX, because that way I only have a single comparison, a single variation of comparison. I don't have to say, all right, if operand 1 is an integer, then put it here, otherwise put it into RAX. It makes it less complicated if you just have one way to translate every instruction in your input language. So anyway, there's the template that you can use. And turning this into C++ code is actually not that hard. So once you have this template and understand it, then you just code it up. You just implement code that will spit out, move, whatever operand 1 is, whatever operand 2 is, etc. Questions on this? All right. Let's look at a complete example of the original code snippet that we were trying to translate. So it was an if go-to, followed by x equals 11, followed by the label, followed by x equals x plus 1. So that was our original snippet that we were trying to translate. Here's what the assembly will look like. So to translate this part, we first have to get the operands. So this is just moving into this is populating RAX and RBX. And the operands are x, which remember we get from the symbol table and an offset from this base pointer. The other operand is 10, which we do an immediate move into RBX for. Questions on this part? All right. Then we do our compare. This compare, if you set up your registers the way I recommend to you, this will just be literally hard-coded. You print out compare every time you see this simple IR statement. And finally, you do your jump if less than or equal to. So this branch with condition code, you just select based on whatever this operator is. So whatever operator you see in the input, you check it and print out the corresponding jump instruction. And then you just literally copy this label here to the label. Questions on that? So that's the complete if go-to statement translated to assembly using our pattern. All right, so x equals 11. This is from getAssign. So it works very similarly. We have whatever the input was, whether it was a variable or a constant, put it into RAX, and then move RAX into the destination variable corresponding to x. Questions on that? That's, I think, review. False label is really easy to translate. It's just identical. It's the name of the label followed by colon. And then we have our arithmetic operation here, which is going off the screen a little bit. So this is a review from last time. So similar kind of template. We take each operand, move it into RAX and RBX. So there's one, and then we pick our opcode based on the operator we saw as input, and then we save the result into the destination. So RAX is the result of the add. We save that into our destination variable. And there it is. There's your complete translation of this 4 lines of simple IR into assembly. Not too bad, right? Not too bad to do it. So if you can do this, you can actually write a compiler for which is actually a Turing-complete language, a language that you can compute any computable number in with this simple IR language. Oops. All right, questions? Oh, yeah.
I'm assuming this is going to get more complex, but can we also represent strings in assembly as well, like the print statement or something like that?
Oh, that's a good question. So so first of all, how are strings represented? ASCII, right? So they're just integers. So as long as you have integers, you can represent strings. So the only thing that distinguishes, just like we talked a little bit about types before, the only thing that makes some binary encoding have meaning is the operation you do on it. So if you take a number and you have a routine that will draw pixels on the screen corresponding to ASCII codes, you've got a string. So I mean, I guess a string is also like an array as well. So if you have an array, what does an array mean? An array is just a pointer. That's all an array is. But if you use it to index into it, and then you take whatever those values in the array are and print them on the screen as ASCII values, voila, you've got an ASCII code. But at the architecture level, the machine, there's no instructions at the architecture level that are like, this is a string, process this as a string. They're just integers. They're just like 8-bit integers. That make sense? All right, questions about this example at all? Okay, so that's everything you need for CodeGen 1. So before I get into some more advanced stuff, let me go over the CodeGen project so you can see how you can actually write the C++ code to do this. It's all in this. Handbook, but let me go over a little bit the C++ part so you can see what's given to you. I think I've got guidelines here. All right, so this is the syntax of the operation statement. So these are this is your arithmetic statements. So don't worry too much about the syntax of how the grammar is specified. But this is how, using our ANTLR parser framework in C++, this is how you access each piece of our template. So remember, the way I described this was each of these instructions has a corresponding template. Actually, this is in, let me go back here. So I updated this to actually add a template for you. I didn't show this last time, but I added it to the notes. So this is what your template looks for arithmetic. And I've given you the exact like object-oriented statement you need to run or to write in order to get each piece of this template. So the destination variable can be accessed with this object. The left operand can be accessed with this object. The operator can be accessed with this, and the right operand can be accessed with this. So I've given you how to get each piece of this syntax from the input. And then for operands, I've given you a function that will translate the operand into the assembly operand for you. So that's done for you as well. So this is written, the code is up here. This will give you the assembly operand for you. It'll already combine, it'll either do the immediate value or it'll give you that RBP offset. It'll just do it for you. It'll do the symbol table lookup for you. So you don't even have to do that on your own for the operands. For the operator, I've given you the enumeration for each of the different operator types. So all you have to do is compare this operator value that's from the input with the operator enumeration. So that'll let you see which operator is being used, and then you can use that to pick which opcode to print out, one of these 4 opcodes. And then for the destination, you can use the symbol table lookup, I think, Yeah, you'll just do the symbol table lookup, which is also described in this document, to generate the appropriate assembly operand for the move, for this final move. Questions on this? Yeah.
How many files do we have to select?
How many files?
Yeah.
So yeah, this was an issue with the proc project. So I think this is spelled out a little bit more explicitly, and I have more warnings here. So you should submit a project that we can clone and build and run. So whatever files you need for it. It's because I'm not sort of dictating exactly how you want to structure your project. But for this project, there's a whole bunch of starter code. Where is this? Oh no, that's the handbook. Where is submitting your project? preparing and submitting your project. So I've given you a template code for this. I have a warning here to include all the files from the project template in your repo. And you can validate this by doing the self-check. So the self-check is in here as well. So if you run these steps, I mean, this is an abbreviated version of it. Look at the Hello project for more detail. But you should be able to clone your project in a new directory. And that's exactly what we're going to do. We're just going to clone it, just like you would do from GitHub or GitLab. And then we're just going to run make and then try to run your program. So this is how you can verify that your repo really is working as expected. I mean, you can do it in Git as well. The VC project shows you commands for inspecting what files are in your repo. But this is how you can do it, like kind of a black box testing. You just clone and build your project, just like any professional software product you would do for any professional source code project. Does that help answer your question? So the template code is more extensive in this project because of the parser framework that I've given you. But that's how you would do it. That's how you can check to make sure it works properly. And you can do that for proc project as well, or any project. Other questions on the project? So each of these, where's the handbook? Each of these functions that you have to write for the various CodeGen projects, they're all detailed here. I've given you like what you need from in C++. You know, what you need to compare to, how you get the operands, like in the arithmetic operations. So you don't have to like guess at any of the C++ or guess at any of the parser framework stuff. You just have to take these coding templates and actually like write them in your compiler so that it will generate assembly correctly. Then do, of course, all the testing to make sure it works properly. Not just our tests, but write your own tests as well. Other questions on the project? So I think the hardest part is really wrapping your head around the compiler idea, that you're taking in a program and you're spitting out a program and they have to be equivalent. I've tried to make the coding part as seamless as possible here because, you know, I know you're not required to have C++ for this class, so I'm trying to take all that out and giving you the parser framework so you don't have to do parsing like in the shell project. But the main concept part is I have the simple IR program. You should know what it does. You should be able to trace through it. And I've generated this assembly program. You should also be able to trace through it or at least run it to make sure it's doing what it's supposed to do. So there'll be a lot of like frustrating gotchas, like you'll miss some little thing in assembly or maybe you'll have a syntax error in assembly. That's what makes this really tricky. You're working with these multiple languages. All right, other questions on the coding project? All right, so let me quickly show you one last thing that, especially if you're interested in security or reverse engineering, might be interesting. So this is the control flow graph for a typical if-then-else statement, a non-obfuscated if-then-else statement. What about an if statement? How might you guess the control flow graph for an if statement might look like? So we've got the condition block here. We have the body of the if statement. And then we have the code after the if statement. So it looks just like the if-then-else statement, except we only have one block inside. So it'll read the condition and either skip the entire if statement or go into the body and then go to the code after the if statement. So that's the if statement. What about a while loop? So let's say I have while x is greater than 0, x minus minus. What about an if statement? So what would an if statement look like? Oh, no, not this again. So for an if statement, we've got our condition check in one block, we have our body in another block, and we have the code after the if statement in another block. So a while statement looks identical to an if statement where we either, almost identical to this statement, where we either go into the body or skip the whole loop. Make sense? The difference is a while statement is basically just an if statement with a go-to that always goes back to the condition check. So you have this cycle in the control flow graph. And you can even see this by rewriting the if statement using goto. So an if statement is nothing more, at least at the assembly level, than a while statement is nothing more than an if statement with a goto. So this is equivalent to this while loop. And you can kind of see that in our control flow graph because this thing has the shape of an if statement. Actually, did I mess this up? Yeah, I think this is right. So it'll never go from goto head to print X. Yeah, so same thing, same shape as an if statement, except inside the body we have an unconditional goto to the top of the while loop to recompute it. Anyway, so control flow graphs, really basic intro to control flow graphs. Let me know if you have any interest in like reverse engineering, decompilation, control flow analysis. I'll send you resources. Or take a compilers class or a malware analysis class and I'll talk about this. Anyway, have a good one, everybody.